So last time we talked about the magnetic force and found a way to find the magnitude for the magnetic force. Now we need to do the same thing for the magnetic field. Now we're talking about the induced magnetic field. So we want to find a magnitude, quantitative value for the magnetic field that's being produced by a charge moving through a wire. So here we're not going to have that external magnetic field. Instead, we're going to look at the wire itself and the magnetic field that's produced by the wire when a current goes through it. Now, this was all done about the same time that this effect was discovered. There were two French physicists who were trying to figure out what was going on and exploring the different things that it could possibly depend upon. And one of the things you as an engineer or a scientist need to be able to develop is the idea of physical intuition. And this is the idea that you can look at a situation, you can say, okay, well, I don't know what the equations are for this, but I know that it has to depend upon this, this, and this. And probably because this is directly proportional, this is inversely proportional, and you can come up with a rough relationship. And some people call that a zero order approximation. So basically, it's not a number that you could actually use. It's something that gives you an idea of how things change with that. Other people refer to it as a back of the envelope calculation. And so the idea is that you can do something quick, dirty in the field and get a reasonably good idea of what's going on. So let's take a look at the microtask and let's see if we can come up with an expression that will allow us to determine the strength of the induced magnetic field from a charge carrying wire. All right, let's get started. Okay, so we know that there are probably going to be three things that are involved, and a lot of this was done from the experimental work of Biot-Savart that was done. But if you think about it, it should probably make sense. So the induced magnetic field must depend upon the current, how much charge is going through there at what rate. It's also going to depend upon the length of the wire. And if you think about it, we're going to get a different amount of magnetic field from a long wire than we will from a short wire. And then finally, it's going to depend upon how far away from the wire we are. And again, that should make sense. When we're close to that wire, we should feel the strongest magnetic field. Farther away, it should get weaker and weaker and weaker. Otherwise, you're going to be affected by the magnetic field of Jupiter affecting you because you're still a long, long way away from it. So let's sit down, pause the video, and figure out which is going to be directly proportional and which are going to be inversely proportional for each of these characteristics. Pause the video, do that now. Okay, so hopefully you've already got this out, but how did you feel that the induced magnetic field would depend upon the current? Probably this one was the easiest. The more current I have, the more magnetic field I'm going to have. So they are definitely going to be directly proportional. So we'll go ahead and circle that one. Now, how about with the length of the wire? Well, it wouldn't make sense to think about, oh, well, I've got less wire, so then I'm going to have a stronger magnetic field. Again, carry it to the extreme. If I have zero wire, zero length of wire, do I have any magnetic field at all? So that tells us that this also must be directly proportional. Last one might be a little bit trickier, but we've seen this kind of thing before. As I get farther away from the wire, so as my distance increases, what's going to happen to the strength of the magnetic field? Well, as we said, it's going to have to decrease. Otherwise, you're going to feel the magnetic field from Jupiter and everything's going to be flying off into space. So since they're moving in opposite directions, then they're going to be inversely proportional from that. So now all we have to do, now that we've got the basic ideas that we need, this back of the envelope calculation, we're going to just put them together and we're going to see what we get. All right, so let's go ahead and delete this page. Go ahead and move on to the next page. And we'll scroll up to where you can see it. Okay, so we've done this many times before. Go ahead and put together what you know and come up with some sort of expression for the magnitude of the magnetic field based on just those three properties that we've talked about. You got it? Okay, well, you should have come up with something similar to my magnetic field, which is a vector. Remember, it's going to depend upon the current in the top and the length of the wire in the bottom, or also in the top because it's directly proportional. And then my distance away from the wire, which is also going to be a vector, must be in the bottom because it's inversely proportional. Now, never forget, we have a constant of proportionality. Anytime we're doing this kind of inversely and directly proportional, we always have some sort of constant that usually has to be determined experimentally. The other thing that we have to think about is how do these things vary? Now, many things that we've talked about up to this point is very linearly, which means to the first power. But lots of forces, and particular things that we found don't. For example, gravity depends upon 1 over r squared. The electric force depends upon 1 over r squared. And oddly enough, lots of things in the universe seem to depend upon 1 over r squared. So in this case, we don't know without doing an experiment how each of these vary. But again, thinking about our zero-hour approximation, our back of the envelope calculation, we've got a pretty good guess that it has to depend upon 1 over r squared. And if you do experiments as they did at this time, then you're going to find out that that's true. So if we modify our expression, all we need to do is then add that squared term there. All right. So that gives us a general expression, but we want to modify this to find it at a particular point. And so look down on the page here. So if I want to find the magnetic field at this particular point P that you see right here, due to that wire, then I'm going to have to add up the contributions of all the little pieces of the wire. It's not just this little piece that's directly here. There's a magnetic field everywhere, and that's all so we've got all these loops of magnetic field, right? And they all add up at this point to give us the total magnetic field at point P. So we've taken care of this before. It's calculus basic class. All we need to do is just take one small little chunk of wire, that dx part of the wire, and then integrate along the entire length of the wire. Now, the wire has a length of L, and we're going to approximate it to be infinitely long. Now, remember, nothing is infinitely long. What do we mean mathematically when we say something is infinitely long? We don't mean that the length is actually infinity. We mean that the length is much greater than the distance. And so you can't see the ends of it, is what that basically means. And so in most cases, that's going to be true. I mean, it's pretty rare for us to be so far away that we're a significant fraction of the length of the wire from that. If it's not true, okay, well then now we're not going to go from infinity to infinity from this. Okay, so as we see here, our total magnetic field then is just going to be adding up all of those little pieces. So we're going to find the dB using the expression that you just derived from that. All right, so on the next page, on microtest 3, we're going to start that process. So let me find my mouse here. There it is. So go ahead and look on the next page here. So the magnetic field is a vector. So we know that it has a direction. What is the direction of the induced magnetic field? Let's redraw our picture here so that we've got it. So I've got a current carrying wire. My current is going in this direction. And I want to know what it is up here at point P. We'll use right-hand rule number 1. So remember, take your thumb, point it in the direction of the current, and then grab that wire, and you'll see where that goes. And in this case, it's going to be into the board. So it's going to be into the page, like we see right here. And that's, of course, true everywhere along here, but we're only going to be focusing on at point P there. So at point P, my magnetic field is going into the board, into the screen that you see here. So that's going to be my B. That's the induced magnetic field. Don't forget, what is it down here? Well, it's coming out of the page because it's actually a loop that goes all the way around like this. All right. So let's go back and get rid of those. There we go. Okay. Now we know that, so this is going to be into the page. Now we know that we have 2 vectors here. And so we're going to have to think about how we can multiply those 2 vectors. We know that we're going to have a cross product at some point in here because we know that the magnetic field itself is going to be a vector. So how do we move on from here? And so we've listed, it's a good idea to just kind of list everything that you know at this point. It'll give you some ideas. So we know that the current is a vector that points along the wire. It's going to be important. So the direction of the current has to be in the direction of our dx. We're going to use that in just a second. The current is the same everywhere, and that makes sense. I mean, we talked about that last time. If we have an electric circuit, then the current through one loop is going to be the same throughout, and that's conservation of charge. The direction of the magnetic field depends upon the direction of the current in space. So again, that's our right-hand rule number 1. Depending upon which direction my current is going, I'm going to get my magnetic field to be in a different direction. And as we found before, the total magnetic field depends upon the total length of the wire. The longer the wire, the more magnetic field I'm going to have. Let's see if that makes sense at point P. If this is my point P, and I've got a very short wire here, well then only those pieces are going to add up to give me my magnetic field. As I extend outward, there's going to be more and more and more magnetic pieces of magnetic field adding up at that point P. So this last then, as we mentioned, the wire is always in the same direction as the current. This is what we have to be able to do in order to do the integration, because I is our vector, our current is our vector, but it doesn't make sense to talk about di because the current is the same everywhere. So instead, we can talk about I, the magnitude of I, but in the direction of dx, the distance along the wire that we're moving. So let's see if that makes sense to us. So let me get my pen back. Here we go. So here's my wire, and here's my current. It's going this way. Right? Here's my point P, and I'm looking at some little chunk right here. This is my dx. So if I started from, perhaps 0 would be right underneath the wire, might be some convenient thing, and this would be minus infinity, and this would be infinity. As I move along, this is x, and I'm moving along that direction. So x is technically a vector because I'm moving from minus infinity to plus infinity right here. But you should see that that direction x is always going to be in the direction of I. And so what we can do is we can, as we point out here, we can use the magnitude of the current I instead of the vector. So our vector I is actually going to be the magnitude, but it's going to be in the direction, or di, for example, if we were going to use that, would be in the direction of our x from that. This is kind of key to solving the whole problem. If you can't see this, then the rest of it doesn't make any sense. Keep back and remember, it doesn't make sense to integrate di because I is constant. It's the same all the way through. You're not going to get anywhere with it. However, I can talk about an infinitesimal dx, and it happens to be in the same direction as I. So that's what we're going to do with that. All right, let's erase what we've got here. Okay, so scroll down to the next microtest. So we're about halfway there. So we have been working on an expression for dB. So let's write down everything that we know about dB right now. So we know that dB is a vector, and we know that it's this constant of integration that we haven't figured out yet. And then it's going to be I, the magnitude of I, dx, which is a vector, divided by r squared. And r squared, r is also a vector in this case. So make sure that you follow along with that. Make sure that that makes sense with what we had before. So let's see, so this dx, remember, you may say, well, where's the L? Well, that's where the dx is coming from, right? So if I've got my length of my wire and I integrate this dx from, for now, let's make it from 0 to L. Do you see that if I integrate that dx across there, then I'm going to get my L. So that's where the dx comes in. The only thing that I've done differently is instead of talking about a vector I and a scalar L, I'm talking about a scalar I and a vector dx. I can't use L because L is going to be the total length of the wire. All right. If that doesn't make sense to you, stop the video and think about that, and maybe even make a discussion post asking for some clarification, because that's not easy. That's not something that you may have run into before, but it is very, very important. So our small little chunk of magnetic field is due to that small little chunk of wire, the current going through that small chunk, which is the same throughout the whole wire, divided by how far away we are, the square of that distance. And if you think about it, the direction of that r makes a difference as well. So if I had, let's draw our little picture back that we have. So here's my P. This might be my R. And so you see that R is not the same as my distance away from the wire. R is going to change as I move, as this is my dx. When dx is right underneath, sure, R is equal to D. But the further along this wire I go, the longer R is going to be. So these two things are not the same. This is a vector because it's pointing in a particular direction. And that direction, you should be able to see, is going to change as I move along there. So I might have a little bit of a problem that I've got to work with this, because I've got two vectors here. I've got a dx and I've got an r squared, both of which are vectors. So I know I need to do some sort of cross product, but I'm dividing. I'm not multiplying. So this might have been something you haven't seen before. Hopefully you have, but just in case, we should probably review that. All right, go ahead and look on the next page. And we're going to take a little diversion here to talk about how to divide vectors. So we do this using the concept of the unit vector. Let me get rid of my chicken scratch over here. So we do this using the concept of a unit vector. And we've used unit vectors up to this point. We've talked about the unit vector I hat as being a vector, say, in the horizontal direction, and so in the I direction, but has a length of 1. So the magnitude 1 times that direction gives me my unit vector. There's another way that I can define the unit vector. I could take any value, any vector, and let's just take a general vector here, v, which has its magnitude and its direction. If I divide by the magnitude of that, all that's left is the direction of that vector. Let's stop and think about that. Take any vector. It's got a magnitude and direction. If I divide out the magnitude, the only part that's left is the vector. That is, by definition, the unit vector, which we might call v hat from there. So we can use either one of these forms. Both of these, both this and this, represent the unit vector. That means there's 2 ways that we can write a vector in this notation. So if I have this vector v, and again, it might be the velocity. In this case, it's just a general v. I could write this as the magnitude of v times the unit vector. And that should be pretty obvious that that works, right? Because my magnitudes cancel. And so then I'm left with just the vector. It doesn't really change anything. A way that might not be quite as transparent mathematically, but kind of makes more sense physically, is to do it this way. So I've got my vector has a magnitude and direction. Here's the magnitude. Here's the direction. Done. Lots of people prefer the first form, the capital V over lowercase over v, or the vector v over its magnitude, because it's obvious how that's going to work, right? This is maybe a little less transparent. However, this form is much easier to write. I have another complaint with the first form. So let's take a look at this next part. Go down 1 to microtest 5. How would we write the magnitude of 1 over r squared? Vector 1 over r squared. And we give you a hint, don't overthink this. Well, yeah, it's just going to be 1 over r squared, right? That's the magnitude of it. That's our vector. That's an r. Okay, so now if I want to write this in vector notation using the unit vectors that we've just defined, there's 2 ways that I could do this. I could say 1 over r squared as a vector is equal to the magnitude, 1 over r squared, times this r hat divided by r. Do you see that r vector divided by r? Do you see that if I have this vector r, I divide by its magnitude, then that is going to give me the direction. So that is our unit vector. This, if I multiply it out though, gives me this over r cubed. Well, that's troublesome. And it's not wrong, because if you look at the units, r has units of meters, r cubed has units of meters cubed, so I'm left with 1 over meters squared, which is exactly what I started with. So it is correct, but it's a little deceptive because it makes things look like things are depending upon r cubed, when in fact we know that they're depending upon r squared, and that's actually what's going on here. So the other form, if this is my vector r squared, then simply becomes 1 over r squared in the r hat direction. And if we really want to get compact with that, we could even write that this way. So I have the magnitude 1 over r squared, and it's in the r hat direction. So this second way is the way that we're going to do most of our classes. This is what we're going to do just about everything that we do, simply because I find the 1 over r cubed notation to be kind of confusing when you're trying to figure out what's going on with this. However, you're going to see a lot of professors, a lot of textbooks, they're going to use that r hat over r cubed. So you really do need to accept it. You need to understand how it works. But for us, since we're still in the very early part of our learning here, we're going to stay with r hat Just take the magnitude, multiply by the r hat direction, and you're good to go. All right. So now let's go down to the next microtask here. So now we've got everything that we need to write our cross product. So what I want you to do is go back through your notes, pause the video, because there's a lot of little pieces that we have to put back together here. Pause the video and give me an expression for d vector b. Pause the video, do that now. Very important you do this. Okay, did you pause the video? Do you have it? Okay, so putting all our pieces back together then, I have that db, which is a vector. Remember that we've got that constant of integration right there. And then I'm going to have scalar I, and then my cross product is going to be dx crossed with r hat over the magnitude of r squared. You see how we've done that here? So I've got two vectors, I've got dx, and I've got r hat. So crossing those makes sense from that. But then it also keeps all of my proportions, r squared and all that, the same. So you're going to find that this is an easier way for us to do this. Okay? All right, so let's take that expression then. And if you look on the next page, then they did some experiments. They figured out what that constant of integration is. And it turns out that that constant is going to be, it's going to depend upon the permeability of free space. And the permeability of free space is written as mu naught. Remember, our permittivity of free space was epsilon naught. And that has a value of 4 pi times 10 to the minus 7. And then the units are written there for you. Don't worry too much about that. That's Tesla, which is the unit of magnetic field we're going to see. Meters per ampere for that. Now, this is one of the 3 fundamental constants of the universe, and this basically governs pretty much everything that happens in the universe. There's the permittivity of free space that determines the strength of the electric field interactions. Then we've got the permeability of free space here, which determines the strength of the magnetic field interactions. And then finally, we've got G, which is the gravitational constant and determines the strength of gravitational field interactions. From that, we can derive pretty much anything that we want to do from that. Okay, so when we work out that constant, the constant here, C, ends up being equal to mu 0 over 4 pi. Now, you can justifiably say, well, Dr. K, isn't that just e to the minus 7? And you're right, it is. However, because of some of the integrations we're going to do later, we're going to find that that 4 pi is going to end up, if we keep it there, it's going to end up canceling out. It's going to help us keep up with a lot of things a lot easier. So instead of writing it as just 1e to the minus 7, we're going to keep it as mu 0 over 4 pi. But then this is a new constant that you should add to your flipbooks and you should have available along with all of the rest of them. All right, let's go to the next page then. And I'm going to erase our old work here. There we go. Okay, so now we've got our final expression, so we're ready to integrate it. So let's write it out in integral form. So we have b, it's got to be the integral of our expression for db. So that's going to be the integral of mu 0 over 4 pi times I dx vector crossed with r hat divided by r squared. All right. Now, we can simplify this a little bit. If we need to talk about our limits of integration, remember we assumed from the very beginning that we have an infinitely long wire. And specifically, that means that the length is much greater than the d, the distance above it that we're evaluating. So this would be integrated from negative infinity to infinity. All right. So both the mu 0 and the 4 pi, of course, and the I are all going to be constants. So we can pull them out of the integral. And so we can simplify things a little bit by doing that. So we're going to say mu 0 over times I over 4 pi times the integral of minus infinity to infinity of dx vector crossed into r hat over r squared. And that's our final form. Now, we can't integrate that unless we get rid of those cross products. Remember, we have to always put in our magnitudes. So looking down at the next part, we can use our definition of the cross product to get rid of it. Now, I'm going to rewrite this here just so that we've got it in one place. This is what you should have in your flip books. This is the actual Biot-Savart law. Integral negative infinity to infinity of dx vector crossed into r hat over r squared. And you, as I'm pointing out here, you already know the direction of b. So now we just need to figure out how to get the magnitude. So we can't integrate vectors, as we said. We have to be able to, well, okay, not with what you know, but we're going to have to get the magnitude form of that. So remember the definition of a cross product. So if I have two vectors, a cross b, then that's going to equal the magnitude of a times the magnitude of b. And then what is the trig function here? That's going to be sine theta, just like that. All right, so we can take that and we can put it back up into our integral so that we can get rid of our cross product. So let's do that here. Let's go ahead and keep that integral where we can see it. There we go. All right, so then we get the magnitude of b, because I've gotten rid of the vector sign here. We know what the direction of b is. We use our right-hand rule for that, so that's not going to be challenging. And so that's going to be mu 0 I over 4 pi times the integral from minus infinity to plus infinity. And then I'm just going to have dx times r hat sine theta divided by r squared. All right. So see if that makes sense with what we have so far. Okay, so we've taken this and we've combined all of this, and one more small simplification that we can make. Remember that I want to use the magnitudes of this. Well, what is the magnitude of r hat? It's just 1. So this is going to simplify just a little bit more, and that's going to give me mu 0 I over 4 pi, and I'm going to write all this integral down again. And in this case, it's just going to be dx sine theta over r squared. And for those who really object to not having the dx at the end, you can obviously just move it over there, but it's going to be the same thing with it. Okay, so now comes the fun part. We need to integrate this, but r depends upon both theta and x. Look at our diagram here and see if you can tell what that is. So if this is theta, this is the angle between r hat, and this is our dx here. Remember, r hat is going to be in the direction of r here. So as I move outward, r gets longer. As x changes, r gets longer, and the angle gets smaller. So as this is, r is certainly not a constant. I have to figure out how it depends upon x. And, well, we can just use some simple trig with that. I'm going to make this a little bit bigger so that we can see it. This is my d, and then we'll call this x squared, and this is going to be our r. Well, r is simply the square root of, x squared plus d squared, if that went through. Okay, so we can take that then, and we can put it in for our expression and with our r squared. Now we also need to get rid of our sine theta. So this angle here is going to be theta. So my sine theta then is simply going to be, let's write that up here, sine theta is going to be what? It's going to be d over r. So now I have what I need. Remember though, I'm going to do this in 2 steps. I've got an r here, so I'm also going to plug in here for the r. Let's look on the next page and let's see if we can put all of that together into one big piece here. All right, let's just slide this down to where we can see it. Okay, so let's sum up our expressions that we found so far. So r is simply the square root of x squared plus d squared. And then sine theta, we said, was going to be this expression over here, is going to be d over r. So now we need to put them back into it. And we give you a little hint that d is a constant. It's a fixed distance. It's that this is the distance at which we're trying to evaluate. It's the distance to point P. So it's not a variable. That's nice. That keeps things nice and simple for us. So let's write our original expression up here. So we've got b, the magnitude again, is going to be mu 0 I over 4 pi. And then integral minus infinity to infinity. And we're going to have dx sine theta over r squared. All right. So let's plug in what we've learned up here. And we're going to get a rather complicated integral that we have to do. But it is in fact doable. So that's going to be mu 0 I over 4 pi, integral negative infinity to infinity. I'm going to keep my dx because I'm going to need everything in terms of dx. So this is the part that I'm going to convert. Well, my sine theta then is d over r, and that's d, the distance d, not the differential d, is d over r. My 1 over r squared then is going to be 1 over x squared plus d squared, because when I square that square root, it just goes away. And then all of this is times dx. Now I'm not done because I still need to get rid of this r. So let's do that on the next step. So then I get mu 0 I over 4 pi, integral negative infinity to infinity, d over square root x squared plus d squared times 1 over x squared plus d squared dx. Well, we can combine these two. So our last little step and the last integral that we need to do is constant, of course, is going to be the same. Integral from negative infinity to infinity. And it's going to be d over x squared plus d squared to the 3 halves dx. See if that makes sense? Take a look at that. Now what can I do with the d in the top? Well, I can pull that right out, right? This is a constant, so I can make that 1 and I can put my d right here. Can I pull this d out? No, I can't, because it's in this parenthesis right here, so it's intimately tied up with the x squared here. So I can, though, make this a 1 and put my d out here. All right, so this then is the expression that we're going to have to integrate in order to get our final expression for the magnetic field, the magnitude of the magnetic field due to that current carrying wire. And it's doable. You can absolutely do it with U substitution. I gave you some clues in here as to how to do that, and it's probably worth doing. But remember, an efficient engineer is the best engineer. So if you've got a software package that will do it for you, and Wolfram Alpha, for example, can do this very easily, then you simply plug it in and you have Wolfram Alpha do the work. Your boss is not going to be impressed that you can spend an hour doing U substitution. It's just not worthwhile. Your boss wants you to get to an answer. And so you use the tools that are available to you. I know that's anathema in your calculus classes and maybe even some of your physics classes. They want to see, can you actually do all of this? If you're a theoretical physicist, maybe. Even if you're a theoretical physicist, you're probably not going to take the time to work out an integral that you can simply plug into Wolfram Alpha and get the final answer. So it's worth doing, but we're not going to do it here because it will probably take 30 or 45 minutes for us to do that. But follow along and see if you can do it. See, just one time in your life, you should probably see if you can actually make sure you can actually do this integral so that if you ever need it, you've got it available. But we're going to press on and we're going to assume that we've put that into Wolfram Alpha and we've gotten our final result from that. All right. When we do, this is the final result, and it comes out something really nice and easy. So this finally is the expression for the magnetic field due to a current carrying wire. And this is something you're going to want to write down in your flip book so that you have it available, because under no circumstances do you want to have to go and do this derivation again on an exam. You do need to keep up with what assumptions we may go in here. We assume that we have an infinitely long wire. Notice that the L has gone away. There's not going to be any L in this expression. That's good because L is infinity. So if those conditions do not hold, and remember our condition is that L must be much greater than D, then we've got no choice. We've got to go all the way back to our integral. And now instead of integrating from negative infinity to infinity, you're going to integrate from 0 to L, for example, something like that. You also need to look very carefully at the assumptions that went into your integration itself. But for many, many cases that we're going to encounter, this condition is going to be true. And so when it is, we get a nice, beautiful, simple expression for the magnetic field, the magnitude of the magnetic field due to a charge carrying wire. The direction, remember, still comes from that right-hand rule number 1. So that's easy. You can do that right away. So there's no reason to keep up with matrices for cross products and things like that. Okay. So now the hard work's done. And the units of the magnetic field we mentioned here is a Tesla. And like I said, no, not the car. The car was named for Nikola Tesla. And one Tesla is an extremely strong magnetic field. A typical bar magnet, like some ones that you've seen in class, has a magnetic field of maybe a tenth of a Tesla, something like that. Earth's magnetic field is actually very weak because it's about 50 microtesla. So for normal everyday use, we will typically define a unit that's smaller called the Gauss. And 1 Gauss is 0.0001 Tesla. So using that, then we can get kind of more reasonable numbers when we're talking about the size of a particular magnet, or if we measure it in Gauss as opposed to Tesla. But understand, they're the same units. They're both units of magnetic field. It's just one of them we've multiplied by 0.0001. That's it from that. Okay. All right. So now that we've done all that, let's actually use this. So we're going to zoom out here and let's look at the scenario. This is the scenario that we've run into before. I'm going to just delete this. This is a scenario that we've used before. We know what the direction is. We've already found that before. So let's find out what the magnitudes of these magnetic fields are. All right. This would be a good time for you to pause the video and work through it completely, and then see if you get the same result that I get when we do this. All right. Pause the video, work out all the steps, and go from there. All right, hopefully you got it, because you're going to have to do it when it comes time for the exam. So may as well get the practice now, right? All right, so we are given, in this case, let me go back to my pen, here we are. In this case, the quantities that we're given, we're told that the current through wire 1 is 50.0 amps. We're told that the current through wire 2 is 75.0 amps. The distance between them is going to be 20 centimeters, which remember is going to be 20 times 10 to the minus 2 meters. And finally, we're going to need this constant, just for our own reference here, is going to be 4 pi e to the minus 7 Tesla meters per ampere. Okay. Our equation is, of course, the Biot-Savart result. It's not technically the Biot-Savart law. You'll hear people refer to it as that. This is the result of the Biot-Savart law for a current carrying wire, an infinitely long current carrying wire. And that's going to be the expression that we just derived. So mu0 over 2 pi d. All right, at this point, it's pretty straightforward. You shouldn't have any real trouble just plugging in numbers and getting an answer. So let's do that. So our magnetic field due to wire 1 is going to be equal to mu0, the current through wire 1, divided by 2 pi times d. Notice that, let me scroll out so we can see our wire at the same time. Notice that our d is going to be the same for each one of them. So d is the separation between these two wires. We're not looking for the field in the middle. I want to, remember when we did this before, we grabbed hold of the wire, and I wanted to, for example, if I want to find the force on wire 1, I need to figure out what is the magnetic field due to wire 2. And then wire 1 just considers that an external magnetic field. We use our right-hand rule number 2, I be fine, and then I can figure out the direction from that. Similarly, when I want to find out the force on wire 2 due to wire 1, I'm going to need to know what is the magnetic field of wire 1 at that same distance, d. So in one case, I'm going up, in one case, I'm going down, but in both cases, it's just going to be d. Remember, our signs, our magnitudes are going to come out of our right-hand rule, not from any kind of the math that we're doing. We're only strictly getting the magnitudes here. So be very careful with that when you're working through it. All right, so we're just going to plug in numbers here. And my 2 pi here, remember that mu is 4 pi e to the minus 7 divided by 2 pi. And that's why I was saying we will often find that we can simply get rid of these and have a 2 left here. So that's why it's a good idea just to go ahead and leave that 4 pi in there in the Biot-Savart law with that. And then that's going to be times 50.0 amps. And then, of course, it's going to be divided by 20 e to the minus 2 meters. And check my work because I'm not going to check it on my calculator. But see if you get around 5 times 10 to the minus 5th Tesla. Now, we want to find the vector. So let's figure out what this is. This is the magnetic field of wire 1 at the position of wire 2. So grab it. And you should see that at the position of wire 2, this is going to be out of the page. So right here at the position of wire 2, the magnetic field going around is coming out of the page. All right, let's find B2. Again, same thing, but now I've just got current 2 over 2 pi d. So I can go over to here, and I'm just going to simplify this. This is 2e minus 7. But now I've got 75.0 amps, and again, 20e minus 2 meters. And when I worked that out, I got 7.5 times 10 to the minus 5th Tesla. Now, what is the direction? So here my current is this way. So at the position of wire 1, this is going to be also out of the page. Do you see how that works? It's also out of the page. So these are my two vectors. The magnitude, this and this came from our solution to the Biot-Savart law. The direction came out of my right-hand rule number 2, or right-hand rule number 1. So remember, for the net magnetic field then, for the magnetic field between the two of them, then I would have to add them if I wanted to find it at any particular point that's going on there. But in this case, though, if I only wanted to find the force, for example, then I'm only going to need to use that right-hand rule number 2. So this is the magnetic field of wire 1 at the position of wire 2, and the value of the magnetic field at wire 1, or at wire 2 due to wire 1, and follow through the logic with that. We have an expression from our last one of how to get the magnetic force, ILB, right? So I've got the magnetic field. Remember, that's the external magnetic field. So that would be the current due to I2 would be using the B1 external magnetic field. See if you can work through the logic of that. Now, I didn't give you the length of the wires here. At least I don't think I did. No, we did. Actually, each wire is 2 meters long. So from that, then we can actually find the final force with that. And so we know that our force is ILB. So our force on 1 due to 2, let's just go ahead and set it up. We won't go ahead and work it out, but we'll set it up. This is going to be the force on wire 1 depends upon the current of wire 1, but the magnetic field of wire 2. And similarly, the force on 2 due to 1 is going to be the current through wire 2, both wires are the same length, times the magnetic field of wire 1. Multiply all those out, you've got everything that you need, and you can get that final force.